the calendar. Today is Friday, the 19th of February. We are covering class number 9, which is integration by parts. Next class coming up on Monday. Oh, there's a quiz due. Is there a quiz due? No. What am I doing wrong here? Yeah, we have a quiz due on Monday the 22nd. I should probably go get that quiz and hand it to you today, shouldn't I? Yeah. Yeah, so apparently I'm going to give you a quiz, and it's on U substitutions, and you'll do it over the weekend. It's a take-home quiz just like the others. So that will be due on Monday. Today we cover a technique called integration by parts. Monday we cover something called partial fractions. It's another integration technique. And then Wednesday coming up, two things. The project number 3 is due. I do have some copies. Did everybody get project 3? Okay, so that's due on Wednesday. Also on Wednesday is our review day for our very first test, which is coming up on Friday, the 26th of February. So our first test is 1 week from today. The test is cumulative. It is on everything we've done through the semester, including today and including the coming Monday, which means it is not too early to start studying for this test, which is 1 week away. Good sources of problems include stuff from your textbook, the homework problems. If you've done all the homework problems and you want more practice, do more problems from the textbook. Another good source of problems are things in the packet. There's the even more practice sections. So I don't think that anybody has finished every problem that's in the packet. So that's a good source. A good source of problems that I think is often underutilized are the sample test problems, which are at the end of this big packet that I've handed you. We haven't looked at them, and we're not really going to look at them together. We do have that review day, so you might spend some time on that review day doing them, but there are practice test problems specifically for you guys at the end of this packet. Is that true? Tell me it's true. Is it true? Oh, sorry. Did I hand you another packet? Yeah, quiz packet. Yeah, the sample test, the practice problems packet. That's what I meant to say. So they're not at the end of this packet. They're in the practice problems packet. That's the underutilized source of problems. Many of those problems, there are videos on YouTube of either me or my colleague Caitlin solving those problems. So even if you are working on them at 3 in the morning, which you should be sleeping at that time, but if you're working on them at 3 in the morning, you might have YouTube as a resource. Okay, so let us jump in here on class number 9. Rob, was there a question? The exam is going to be on everything from the semester, not just the recent integration techniques. It's going to be more like the homework problems than the project problems. Yeah. Okay, so daily summary. In this class, we learn a brand new technique called integration by parts. It's basically the antiderivative version of the product rule, which we know from derivatives. So let's take a look at number 1. Are we able to calculate the simple looking integral of 3x cosine x dx? 3x cosine x dx. Well, there's one thing you can do to make the integral look a little nicer right away. What's that? Take that 3 and bring it outside. So we're not disturbed by the 3. We have an x and we have a cosine x. If they were completely separate from each other, we could handle them individually, but they are multiplied, and we know we can't just pull one of them out. We can't separate them into 2 integrals. So x times cosine of x. You might try U substitution. That's our only technique for something that isn't in our short list of things we can find antiderivatives for. Thoughts on what you could let U equal? Letting U equal x is a reasonable thing to do, because one of our rules is that if you have a cosine of some stuff, you might let U equal that stuff inside of the cosine. So it doesn't take too many times of students to do this, but letting U equal x has the effect of changing all of the x's to u's, and that's all. And so you will just come up with that integral again exactly as it is, but the x's will magically have turned into u's, which is not helpful. But it's worth trying once just to see that you're never going to try it again. And there really isn't any other natural choice for U. There's no U substitution that's going to work. So this is a pretty simple looking integral, and that little multiplication there makes it so we just can't do anything. So we need a new technique, and here it is. It's called integration by parts. It's got this formula. The integral of U dv is equal to U times V minus the integral of V du. I'm not going to derive this thing. You can take a look at the derivation in your book if you're interested, or see me outside of class. I'm happy to walk you through it. It's not hard, but I just want us to be able to use it. So let's give it a shot with that same integral, 3x times cosine of x dx. So here's the setup. I am going to start with a u here equals and a dv over here equals. And I'm always going to start the setup this way. And our job is to see this original integral in this form. We are trying to use this magical formula. And so I need to recognize the integral I have as being something that I'm going to call u times something I'm going to call dv. And those are the two pieces I've written out here. Now, you got kind of natural choices. I mean, this is a multiplication, and there's a multiplication right there. So it seems like the two natural choices are you either let the 3x be the u, and then the rest of it, cosine x dx, is the dv, or the other way. You could let the cosine of x be the u, and the rest of it be the dv. Turns out one choice is going to work and the other isn't. I'm just going to write down the one that's going to work, and then after we do it successfully, we'll see why the other way is a bad choice. We're going to let u equal this 3x. And then everything else gets put into the dv, which is a cosine of x dx. So even if we don't have any idea what's going on, at the very least, we have got our foot in the door with this formula, right? Because u times dv is exactly what the formula says you need to start with, and the entirety of our integral is now captured in the u times dv. Okay, next thing we're going to do is recognize that inside of this formula is a du, and also inside of this formula is a v, and I'm going to put those two things right underneath here. Du equals v equals. Okay, what calculus thing does du suggest we should do to the 3x? Take its derivative. That's what we're going to do. What's the derivative of 3x? It's 3. Now, I'm going to write something. Don't write this. But really what we're doing is du dx is 3, right? And then we're going to move that dx over to the other side, treating it like a fraction, just like we did with u substitutions. And so I just put that dx over there automatically. It's just part of the process. So it's like two steps in one, but once you've done it a few times, you just write it there automatically. On the other column, we have dv, which suggests that we are looking at the derivative of some function, and we are trying to find v. So what calculus thing should we do? We should do an antiderivative. So the antiderivative of cosine x is sine of x. Be careful with your signs. Technically, you could put a plus c there. It turns out any constant, any choice of constant will work in this formula. We're always going to choose 0, so we'll never put a plus c or anything else out there. Okay, now it's time to start using the magical formula. According to the formula, this is equal to u times v. Now, u times v are always going to live on this diagonal if you set things up this way, which is how I will always set things up. Recommend you do too. So we just multiply those two things together. 3x sine of x. And then continuing in the formula, we just wrote uv. What's the next thing? Minus. What's the next symbol in the formula? Integral. And now we just have to find the right pieces. It says v times du. And if you write it in this way, v times du is always on the bottom. Those two things multiplied. So sine of x times 3 dx. No, the dx is actually, it's part of the du here. So yeah, we don't need the dv, we don't need a dx after the first sign because the formula here starts u times v, which is just these two, and there's no derivative, there's no dx in either of those. The dx is going to come in on this piece, and so it will always be there in the integral. Right? And Coleman points out, yes, the dv kind of gets left out of the party. It's just not in the formula. Okay, so we're actually almost done with this one. I'm going to copy the 3x sine of x. minus, and now we're going to do this integral. Now, integration by parts is just going to trade you the original integral for a new one, and the hope is that the new one is somewhat better than the original one, because you're always going to have an integral to do when you do integration by parts. Still have one left because it's in the formula. Okay, that 3 I'm going to think of as being in the front, so I'll just copy the 3 down. What's the integral of sine of x dx? Negative cosine of x. Here we do need to stick on what? Plus c. And that's our answer. Right? So the 3 came out. We did the integral of sine of x. It was negative cosine of x. We'll just clean this up. 3x sine of x minus minus makes a plus. 3 cosine of x plus c. Now, you have no reason to believe that that formula works, but we can check whether or not that's right. What can we do? Take a derivative, right? This is still, even with the crazy formula, that integration by parts formula, you can check every one of these by taking its derivative. You better get the original integrand. I think it's actually helpful to take the derivative here. I'm not going to ever mandate that you check your antiderivatives, but I think it's instructive to take it. So let's take a derivative. 3x times sine of x. What derivative rule do we need? Product rule. And we had said at the outset, the integration by parts formula is basically the antiderivative version of the product rule. So here we go. Product rule says, so here's our derivative of all of that stuff. So first times derivative of the second. What's the derivative of cosine? Plus, continuing the product rule, second times derivative of the first, sine of x times 3. Great, so there's the product rule. I'll underline that part, and then continuing on, now we're at this part, derivative of 3 cosine is negative 3 cosine, negative 3 sine of x. And then the plus c derivative is nothing. And what happens when we simplify? The negative 3 sine x and the positive 3 sine x cancel. Well, wasn't that fortunate? And we're left with 3x cosine of x, which should make us feel real good because that's the original integrand, right? That's what we were after. It worked. It worked. Okay, let's take a look at, I mentioned that there's a good choice for you in DV and there's a bad choice. The reason this was a good choice is that when we got to the integral, that was this piece right here, the thing was better than it was before. This was the integral that we traded for, right? Why was that a better and easier integral than the original? Yeah, the problem in the original was the 3, that we couldn't handle the fact that there was an x and a cosine of x. Why did that x disappear when we came over to this integral? That's it, right? We let u equal 3x. We took the derivative because the formula says to do that. And that 3 all of a sudden doesn't have the x. The x was the problem. We got rid of the problem. So putting a 3x over here was a great choice because taking a derivative made the 3x simpler, right? It brought the x out of the problem. If we had made the other choice, which is totally legal, I'm going to write this and then we'll get rid of it. But if we had chosen instead to put cosine of x here and 3x dx over here, take a derivative of cosine, it becomes sine or negative sine, it hardly matters. This is the issue. Taking a what to go from dv to v? Take an antiderivative here, right? What's the antiderivative of 3x? 3x squared over 2. Only thing I care about in that is the x squared. And all of a sudden, when we do this integral down here in the bottom row, it's going to have an x squared times a sine of x. That's worse, right? We started with an x times cosine. All of a sudden, we have an x squared times cosine or times sine. It went the wrong way. We made it worse. And so typically, this is just a rule of thumb. You want to put something in the u that gets better when you take a derivative, and something in the dv that hopefully doesn't get too much worse when you take an antiderivative. Mario. I will not get mad at you. I won't, I promise. Okay, let's do another one of these, part B. Integral from 1 to e of ln of x dx. With practice, you guys will start to see that integration by parts is a good thing to think about when you have a product of two functions in your original integral. In the first problem we did, it was a 3x times a cosine of x, and we very naturally split that into our two pieces. But ln of x is not two pieces, right? It's just one thing. It's not like it's one thing times another. So this is somewhat unusual, but it turns out integration by parts is going to work on this guy. And just take a moment to recognize we have no way to find an antiderivative of ln of x at this point, right? It's not 1 over x. That's the derivative. So we're looking for someone whose derivative is ln of x. I don't know, but we've never done a problem where the derivative turned out to be ln of x. So let's set it up in our consistent way, u and dv. And let's go ahead and get the rest of the puzzle up here on the board. What's the next row? du down here and v over there. And again, I encourage you to just write it like every time you're doing parts, just start with that basic shell in exactly that order. And just while we're thinking about it, the formula for integration by parts is going to multiply which two pieces first? So just in the right-hand side of the equation, it's going to be that times that, and then v times du. And sometimes I like to put like a minus integral that way. But that's the basic shell for every integration by parts. Okay, so let's put the pieces in. Here are your two choices. Don't write these because one of them is going to need to go away. You got to put the ln of x in one of those places, not both. If you put the ln of x in the u part, what are you supposed to do to get down here? Take a derivative. Okay, fine. If you put it in the dv part, what are you supposed to do? Take an antiderivative, which is the thing we're trying to do and we can't do. Okay, so we're not going to put it over there. But we do have to put something over there. What's the only thing left? There's the 1 and the dx. dx is always going to be part of the dv. Okay, well, let's give it a shot. So we come down the first column by taking a derivative, 1 over x dx. That always needs to be part of your du. Okay, going down the second column, to go from dv to v, we need an antiderivative. What is it? X, right? Because that 1 becomes a 1x. This kind of breaks the rule that I had said before about you put something in the dv that doesn't get much worse. Hey, x is worse than the 1 that we started with. Well, it turns out things are going to be okay in this one. Let's see if we can continue. This equals. Okay, so now following the green arrows, we're multiplying. This is just the formula for integration by parts. ln of x times x minus the integral. What times what? Yeah. Yeah. All right, we're just multiplying across the bottom row. Yeah, good question. So I'm going to change colors again here. Let's go this one here. So this is still a 1 and an e. And part of why I wanted to put a definite integral here is to point out that ln of x times x, they still need to get replaced with the same 1 and e. So this is the point where we also have to put in that. It's kind of weird because the u times v, that ln of x times x, doesn't feel like we did an antiderivative that we should be plugging in the 1 and the e and subtracting, but it's up here in this hint. This is just how it works, is that when you do that uv, you're still plugging in the numbers and subtracting. Okay, and hey, this is great because the integral of x times 1 over x is just the integral of 1. So things are good. So let's just write our next line here. I'm going to copy the ln of x times x minus. We said this integral was the integral of 1 dx, which is just x. And now I'll put brackets around the whole thing, 1 and e. Okay, so now we'll substitute. Top one goes in, bottom one goes in, and subtract. ln of e times e minus e. Subtract, and then we plug in the 1. ln of 1 times 1 minus 1. Right side. So this thing here. Yeah, so this guy I copied, it's there. And this one we said a lot but didn't write very much. So this guy right here is really just the integral of 1 dx, right? Because the x and the 1 over x cancel to just a 1, right? And what's the integral of 1 is the x. Okay, how much is ln of e? That's 1, so times the e becomes e minus e, super, minus, how much is ln of 1? 0 times the 1, so 0 minus 1, so altogether I think this is just 1.
Is it worth asking why it's not a universally known fact that the antiderivative ln of x times x minus x?
You could memorize it and just add it to our list of formulas, right? I mean, that's Coleman is saying something true. We have just discovered that the integral of ln of x is this thing. It's just slightly more complicated than our basic set of antiderivative rules, so we haven't included it, but it's easy enough to get there. Okay. So on the next page, we see e to the 2x sine of x dx. All right, so it says here in the hint, this one involves something called solving for the original integral, and then my editorializing, it's just plain weird. So I want you guys to get to the activity as soon as possible. And this problem is kind of long if you copy everything down and worry about the details. So pencils down. If you want to see the details, you can check out the video later on. Just focus on big picture. Don't get lost in the details. I'm going to do this one as quick as possible. Okay, you got two choices for u and dv. One of them is going to be e to the 2x, and one of them is going to be sine of x. It turns out it makes no difference which one you pick. I will put the e to the 2x here, which leaves sine of x dx over there. First column, we know we take a derivative, e to the 2x times 2, yes, chain rule. Second column, antiderivative, it's negative cosine. So far, so good. Okay, I'm going to give this original integral a name. I'm going to call it I. You might think it's for integral, but it's for Ian, actually. All right, so there's the integral. We'll call it I. So that means down here, according to our formula, we're just going on the diagonal. So e to the 2x times negative cosine of x minus the integral of, and then we go across the bottom row. So negative cosine of x times this e to the 2x times 2 dx. So all the pieces are where they belong. Super. Let's clean this up a little bit. Equals, I'm going to pull that negative sign in the front. Negative e to the 2x cosine of x. Minus minus makes a plus. I'm going to take that 2 from inside this integral and pull it outside. Look at that. The main idea with integration by parts is that you are trading one integral for one that you hope is easier. So compare the original integral, which was e to the 2x times a trig function, to the new integral, which is e to the 2x times trig function. Well, it's not any better. It's not worse, but it's not any better. Turns out we're going to do this thing again. Integration by parts again. So here we go. Just looking at this integral right here, I'll set up in exactly the same way we always do. I said before you had a choice. You'd either put the e to the 2x in the u or the dv, and it makes no difference, and that was true. Now it makes a difference. We got to make the same choice that we made up above. Where are we putting this e to the 2x? In the u, because that's where we put it up above. If you make a different choice, it's not illegal, but you will get down to something where the original integral is equal to the original integral, which is very much true, but not helpful. Okay, so dv in this case is whatever is left, which is the cosine of x dx. Here we're still taking a derivative. Chain rule again. Second column, we're taking an antiderivative. Cosine came from sine of x. No need for the plus c's here. Okay, and so what are we going to do here? I'm going to go back to black. I'm going to go back to the original integral, which means I'm copying the stuff that we had before. This integration by parts is only what's underlined in blue, so I got to copy the first part. Negative e to the 2x cosine of x plus 2 times. Now we're in the underlined blue, which is the second integration by parts formula. So we go on the diagonal just like we did before. E to the 2x times sine of x minus integral on the bottom row, sine of x e to the 2x times 2 dx. Don't get lost in the details, but some folks confirm we've got all the pieces just where they belong. Okay, we're going to do one last cleanup step and then magic will happen. Here we go. I equals, copying this first term, plus 2 times. I'm actually going to distribute that 2 right now. 2 times e to the 2x sine of x minus, okay, this 2 in the front is distributing to that integral, but that integral has a 2, which I'm going to pop out. 4 integral sine of x e to the 2x dx. Everybody okay with the distributing? Okay, again, we trade one integral for one that we hope is better. How does this last integral compare to the original integral? It's the same. It seems like we're in an infinite loop. And, you know, we end at 1150, so we probably don't want to spend the rest of our time doing this. But it turns out that there's this little sneaky backdoor way to finish this problem. We're actually done with the calculus. The rest of this is algebra. What is a good name for this thing right here? That is I. Yes, that's what I called it. So this equation says I equals some stuff minus 4i. So this is something like this. X equals 3 minus 4x. What would you do? You'd add the 4x to both sides to get all the x's to one side. Super, that's what we're going to do. We're going to add these 4 i's over to that side, giving me, how many? 5i equals, I'm going to copy the rest of this in the front, negative e to the 2x cosine of x plus 2e to the 2x sine of x. All that divided by 5 is the answer, right? So I don't have room to write it again. I'm going to cross it off here and put over 5 here. At some point, you got to put in a, we'll just kind of make it up at the end there. You got to put it somewhere. Sam. Yeah, it's because the sine became a cosine, which came right back to the sine. That's why it happened. Yeah. Okay, I think that it's fair to say, and I suppose I'm bound to it because I'm recording now, I don't think I'm going to ask you on a test to do one of these repeated integrals, but I just wanted you to see it, and you will have a chance in the activity to practice it if we get there. Again, that's not the most important example for learning integration by parts, but I just wanted to show it.
Your only clue
For this repeated one? Yeah. The repeated one worked because it was e to whatever and then times sine or cosine. That's the format for this. Okay, a couple of hints before you jump into the activity. Let's see, integration, this is number 4. Integration by parts is a kind of a way to undo the product rule, and it transforms an integral involving the product of two functions into another integral, which may or may not be easier to deal with. We hope it's easier. Furthermore, integration by parts is good for integrating products of two functions, one of which gets better when you take a derivative, like the 3x became just a 3 when we took its derivative in the beginning, and the other of which doesn't get much worse when you take an antiderivative. Parts is also a good technique to consider when integrating an inverse trig function, like inverse cosine, or a log function. We did ln of x together in this demo. Just a couple of general suggestions for you. You could let u equal ln of x, or inverse sine, or inverse tan, or polynomials, all of which kind of get a little bit different or better when you take its derivative. Suggestions for DV, you're looking for things that don't get much worse when you take antiderivatives. Sine and cosine don't get any worse when you take an antiderivative. E to the x certainly doesn't get any worse when you take an antiderivative. Okay, activity is on the next page. Let's see what we can do.